Yeah, so let's continue with the ideas centering around spectral theorem. And we finished the proof of the spectral theorem. We finished the proof of the spectral theorem, and that was a good place to stop last time. So a small coda. So in the proof, in the theorem, we will find that if you have a matrix a Hermitian matrix, then we got an orthonormal basis of eigenvectors. You string them together, you're going to get a unitary matrix U, and you're going to show exactly as in the previous chapter that U star AU is a diagonal matrix. So AU is AV1 da, 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 AVN, and AV1 is lambda 1 V1 da, 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 lambda n Vn. But this can also be written as, using the basic rule 1, you can check that this is exactly V1 V2 Vn applied multiplied with the diagonal matrix lambda 1 lambda 2 lambda n. But V1 V2 Vn, the column the columns strung together is U. So U star AU is the diagonal matrix. So this is a small, the exact repetition, I repeat, exact repetition of the diagonalizability theorem that we did. So we repeat the same lines again, and it's a coda that since we have an orthonormal basis of eigenvectors, you string them together, you get a matrix U. U is not only non-singular, it is actually unitary. And U star AU is basically the diagonal. A very different proof of the spectral theorem can be given using ideas of maxima minima, and it is available on my homepage. Go to MA207 notes, and if you go to slide number 200 and beyond, you will find the proof using calculus. Okay, let's proceed a little further. Commuting matrices. Excuse me. When two matrices A and B commute, and they're both Hermitian, I'm going to assume that A and B are, excuse me. I have A and B are two Hermitian matrices. I know that there is a unitary matrix U such that U star AU is diagonal. I know that there's a unitary matrix V such that V star BV is also diagonal. And the diagonal entries are the eigenvalues, of course, as we saw just now. The question we are interested is, can you choose the same U and V? In other words, can you find a common unitary matrix which will simultaneously diagonalize A and B? I want the same unitary matrix U such that U star AU and simultaneously U star BU are diagonal. Diag lambda 1, lambda 2, lambda n, diag mu1, mu2, mu1. When can I do this? When can you find this a common unitary matrix which will simultaneously diagonalize A and B? Suppose this happens. Let us call the diagonal matrices D1 and D2. Let us call the first one D1 and the second one D2. Now remember that diagonal matrices commute. D1, D2 will be the same as D2, D1. Always any two diagonal matrices will commute. But what is D1? U star AU. What is D2? U star BU. What is D2? U star BU. What is D1? U star AU. Therefore, U star B must be B U star A. Because U star is non-singular, I can cancel the U star on both sides by pre-multiplying by U, etc. And U star is I. So AB equal to BA. So AB equal to BA is a necessary condition for this simultaneous diagonalization. It is a common unitary matrix which simultaneously diagonalizes both A and B. Now we shall see that this condition is also sufficient. This property is expressed by saying that commuting matrices can be simultaneously unitarily diagonalized. This is what we have proved, that there's a common unitary matrix that diagonalizes both of them simultaneously. The proof involves a few steps, but each step in itself is pretty easy, and we shall break it up into simple lemmas. The first lemma that we want to prove is, suppose if A and B are commuting Hermitian matrices and lambda is an eigenvalue of A. And lambda could have several eigenvectors which are linearly independent. That is, the geometric multiplicity is K. Then we have V1, V2, Vk. And since the eigenvectors, I can always assume that they are orthonormal, because otherwise I can apply Gram-Schmidt. And I get V1, V2, Vk. They are all eigenvectors with the same eigenvalue lambda. Now what happens is that then each of, when I look at BV1, BV2, BVk, each of these BV1, BV2, BVks is a linear combination of V1, V2, Vk. That is, I simply take an eigenvalue lambda and it has some multiplicity, say k, and so I got k orthonormal eigenvectors corresponding to the same eigenvalue lambda. And now I apply the b's to these vectors v1, v2, vk. So bv1, bv2, bvk, each of these is a linear combination of v1, v2, vk. That is, bv1 will be beta 1, 1, v1 plus beta 2, 1, v2 plus dot 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 beta k1, vk, etc. bvk is b1k v1 plus b2k v2 plus dot 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 bkk vk. The matrix beta ij is a Hermitian matrix. So all these things, you're going to prove these two things. You have to prove that the BVI, the BVJ is a linear combination of the V's, and the matrix of coefficients is Hermitian. Okay. So V1, V2, Vk are eigenvectors of A with the same eigenvalue lambda. You simply complete it. You simply complete it on orthonormal basis of eigenvectors, because A is a Hermitian matrix. So I'm just focusing on the first k the k elements v1, v2, vk. They are all eigenvectors of corresponding to eigenvalue lambda, and the remaining eigenvectors are there: vk plus 1, vk plus 2, vn. Fine, they're orthonormal system. And the eigenvectors vk plus 1, vk plus 2, etc. are all not equal to lambda. Eigenvalues, they are eigenvalues they are eigenvectors with eigenvalues not equal to lambda. Lambda is eigenvalue for the first k of them. By the way, this should be lambda k plus 1. Should be lambda. The lambda k plus 1, lambda n. This should be lambda. The eigenvalues corresponding to these eigenvectors are different from lambda. So it should be a k plus 1 here. So BV1, the entire list V1 up to Vn is a basis. So BV1 surely can be written as beta 1, 1 V1 plus da 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 beta k1 Vk. Plus this, the BV1 is a linear combination of the entire list, because the entire list V1, V2, Vn is a basis. So I can write BV1 as a linear combination of basis elements. But the first k of the coefficients are being named as betas, and the remaining have been named as gammas. We have to show that these gammas are not there. Our job is to show that the gammas are not there. So how do I show that the gammas are not there? Let us apply A to both sides. A, B, V1 will be beta 1, 1 lambda V1. Lambda comes out plus beta K1 lambda Vk. Lambda has come out. And so this is what it is. As to the other ones, gamma k plus 1, lambda k plus 1, vk plus 1, da da da, gamma n, lambda n, vn. So we got this for equation number 1. Okay, this is equation number 1. Now, on the other hand, ABV1 is the same as BAV1. And what is BAV1? B of lambda V1. Lambda comes out, and that is BV1. But what is BV1 by hypothesis? The same list. Lambda times beta 1, 1 V1 plus da 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 beta K1 Vk. And then the gamma k plus 1s are all there, but this time they're all getting multiplied by lambda. So now let us call this equation number 2. Now let us compare equation 1 and equation 2. Here the difference is that when I applied A to BV1, and when the A falls on Vk plus 1, I got lambda k plus 1 Vk plus 1. Here, I got lambda gamma k plus 1 vk plus 1. So there's a difference. What we are going to do is we are going to but the first k of them are the same. In the first, the parenthesis here times lambda, the same parenthesis times lambda. Now subtract, what do we get? Left hand ABV1 is the same as BAV1. So subtract, we get 0 equal to, the parenthesis terms goes away. We straight away get lambda k plus 1 minus lambda. Lambda k plus 1 minus lambda, gamma k plus 1, vk plus 1, etc. So lambda k plus 1 minus lambda, gamma k plus 1, vk plus 1 plus dot 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 lambda n minus lambda, gamma n vn. But remember that the lambda was different from lambda k plus 1, lambda k plus 2, lambda n. So these differences of these lambdas are all non-zero. And the vectors are orthonormal. The vectors are orthonormal, so every coefficient must be 0, but the differences of these lambdas are not 0. So compulsorily the gammas must be 0. Gamma k plus 1, gamma k plus 2, gamma n must be 0. And the gammas have been, we have proved that the gammas are not there. So BV1 was assumed to be a linear combination of the full list V1, V2, Vk, Vk plus 1, Vk plus 2, Vn. And beyond Vk, the coefficients were gamma k plus 1, gamma n. These gammas are 0. So BV1 is a linear combination of V1, V2, Vk. Similarly, BV2 will be a linear combination of V1, V2, Vk. BVk will be a linear combination of V1, V2, Vk. Similarly, BV2, BVk. And so the first part of the lemma is done. The first part of the lemma is over. Now we got these coefficients. So BV1, BV2, BVk, we got a bunch of coefficients. You have to show that this bunch of coefficients forms a matrix which is Hermitian. So let's do that. So okay. So let us write BV1 is beta 11 V1, beta 21 V2 plus dot 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 beta K1 Vk. BV2 beta 1 2 B1 dot dot beta K2 Vk. Let us do the same thing. Let us multiply the first one by V2 star and the second one by V1 star. That's what I'll do. So first multiply the first one by V2 star. V2 star will be what? Beta 11 V2 star V1. 0 because V1 and V2 are orthogonal. Beta 21 V2 star V2. V2 star V2 is 1. It's an orthonormal vector. Each of them is a unit vector. And so when I multiply the first one by V2 star, I'm going to get beta 21. And when I multiply the second one by V1 star, I'm going to get beta 1, 2. Correct? But V2 star BV1 and V1 star BV2 are both 1 cross 1 matrices. No? So when I take a 1 cross 1 matrix and when I take a star, I'm going to get a conjugation. No? So V2 star BV1 star is simply V2 star BV1 bar. But left hand side is V1 star B star. B star is B. V2 star star. V2 star star is V2. So we get that V1 star B V2 is the same as V2 star BV1. So BV1 bar. So we got the equality beta 1 2 equal to beta 2 1 bar. We got the equality beta 1 2 equal to beta 2 1 bar. Similarly, beta ij will be the same as beta ji bar. And you can check that beta 1 1 must be real, beta 2 2 must be real, etc. Okay. So lemma is completely established. It's an important stepping stone. So now let us prove the theorem. If A and B are commuting Hermitian matrices, another lemma, if A and B are commuting Hermitian matrices, then there is a vector V not equal to, there is a simultaneous, these commuting matrices have a common eigenvector. There is a vector V not equal to 0, which is simultaneously an eigenvector of A and B. Commuting Hermitian matrices have a common eigenvector. Again, let us take an eigenvalue. Again, proceed as in lemma 1. V1, V2, Vk are you take an eigenvalue lambda of A, If that eigenvalue may have geometric multiplicity k, it may have several eigenvectors. Take an orthonormal system v1, v2, vk, all of them eigenvectors with eigenvalue lambda. All right. And now I want to now take a linear combination c1 v1 plus c2 v2 plus ck vk. If this vector is non-zero, suppose I take a linear combination with non-zero, at least one of the coefficients is non-zero, then this is going to be a non-zero vector. Now apply A to it, c1 lambda v1, c2 lambda v2, etc. ck lambda vk, lambda comes out. So this is also an eigenvector. So this v is also an eigenvector of A. So our problem will be solved. So what are we trying to do? We are trying to find a common eigenvector. We took some orthonormal system of eigenvectors with eigenvalue lambda. Now we are going to manipulate these constants c1, c2, ck such that if you suitably manipulate these constants, then I will be able to find a certain choice of c1, c2, ck such that this combination will become an eigenvector again. So our problem will be solved if we can select the constants c1, c2, ck such that this particular thing c1 v1 plus c2 v2 plus ck vk is also an eigenvector of B. It is definitely an eigenvector of A. I just said it, but we have to select the constants in such a way that this is also an eigenvector of B, and that will be the common eigenvector. That is what we want. We want B of c1 v1 plus da 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 plus ck vk is mu times c1 v1 plus da 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 plus ck vk. This is what we want. But now what do we have? BV. So you have to write. We have to calculate BV1, BV2, BVK. But remember, BV1 was what? Beta 1 1 V1 plus da 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 beta 2 1 V1 plus da 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 beta K1 VK. Remember? So let's put that down. And so you'll get left hand side will be a linear combination of V's, right hand side will be a linear combination of V's. The V's form a basis. Compare the like terms, compare the coefficients of V1, coefficients of V2, coefficients of VK on both sides. You are going to this equation when you put the value of BV1, BV2, BVK in terms of the betas, the whole thing is going to translate to this equation. Square bracket beta ij C1 C2 Ck equal to mu times C1 C2 Ck. What do we know about the square bracket beta ij's? Remember lemma 1, the square bracket beta ij is a Hermitian K by K matrix. And we want the C's to be not all zero. That means it should be non-zero vectors. We want a non-zero vector of C's such that beta C equal to mu C. So what must be this C? No prizes for guessing. We must try an eigenvector. This K, this C1, C2, Ck must be an eigenvector of this beta matrix. But we know beta is a K by K Hermitian matrix. Of course, you can take its eigenvalue, and you can just take the corresponding eigenvector, and that does the job for you. So our problem of finding a system of constants C1, C2, Ck not all zero has been done. The job is complete. The lemma 2 is complete. So we have proved that commuting matrices, Hermitian matrices, have a common eigenvector. Now we are ready to prove the theorem. If A and B are commuting Hermitian matrices, we can find a common unitary matrix U such that U star AU and U star BU are simultaneously diagonal. The proof is by induction as usual. The case of one cross, if A and B are 1 cross 1 matrices, they're already diagonal, and so the requisite U is simply the 1 cross 1 identity matrix. So the inductive base, the case for 1 cross 1 matrices is completely trivial. Assume that the result has been proved for commuting n-1 cross n-1 matrices. Inductive hypothesis. Now take V1 to be a common eigenvector for both A and B. Take V1 to be a common eigenvector for both matrices A and B. We have just proved lemma 2 that such a vector exists. It's an eigenvector, so it's non-zero. I can divide by its length. I can make it a unit vector. And I can, by Gram-Schmidt's method, complete it to an orthonormal basis. V1, W2, da da da, Wn. I don't know what the W's are. The only thing is that this entire list is orthonormal. Now you can guess what the next step is going to be. Cook up this matrix Q by stringing these unit vectors together, orthonormal vectors together. You're going to get a unitary matrix, obviously. And then Q star AQ, as in the proof of the spectral theorem, Q star AQ will turn out to be lambda 0, 0, C1. Similarly, Q star BQ will be mu 0, 0, C2. And as in the proof of the spectral theorem, C1 and C2 will again be n-1 by n-1 Hermitian. But now I got AB equal to BA. AB equal to BA means Q star AB, Q equal to Q star BAQ. Now between A and B, put a QQ star. And you'll get Q star AQ and Q star BQ commute. If Q star AQ and Q star BQ commute, that means C1 and C2 must commute. So C1 and C2 are commuting Hermitian matrices of what size? n-1 cross n-1. So by induction hypothesis, there exists a unitary matrix S such that S star C1S and S star C2S are both diagonal. Now if S is unitary, then 1, 0, 0, S is also unitary. The 1 is a 1 cross 1 matrix. The 0 is a string of zeros, and this is a column of zeros. There's a row of zeros. 1, 0, 0, S, that's also unitary. Call this, now this is a unitary matrix. Q is a unitary matrix. So Q times 1, 0, 0, S is a unitary matrix again. That's a unitary matrix U. Now let us prove that this U does the job for us. U star AU. What is U star AU? It'll be 1, 0, 0, S star Q star. Remember, when I take the star, I have to reverse the order of the multiplication. So it'll be 1, 0, 0, S star, and the Q star will appear on the right hand side. And then there's a A, and then there's a Q, and then there's a 1, 0, 0, S. But the middle one, Q star AQ. What is Q star AQ? Lambda 0, 0, C1. So you've got these three matrices. Do the matrix multiplication. But these three, they are block matrices, if you like. But when you do the product, you're going to get lambda. Excuse me, there's a mistake here again. It should be there's a typo here. This first entry should be lambda 0, 0, S star C1S. Similarly, U star AU will be 1. Sorry, again, it'll be mu 0, 0, S star C2S. But S star C1S is diagonal, remember? And S star C2S is also diagonal. So both U star AU and U star BU are both diagonal, exactly as asserted. So as an application, let us recall that an n cross n matrix A is said to be a normal matrix if AA star equal to A star A. Remember the definition of a normal matrix from the earlier chapter? AA star equal to A star A. Now a matrix is normal means I can write it as A equal to B plus IC, where B and C are Hermitian and BC equal to CB. In fact, what is this B? B is A plus A star by 2. What is C? A minus A star upon 2I. Right? So and those are Hermitian because AA star equal to A star A. So B and C are Hermitian and BC equal to CB. Now, because B and C are commuting Hermitian matrices, I can find a unitary matrix U such that U star BU and U star CU are diagonal. And so therefore U star AU is going to be diagonal. So a unitary matrix, so a normal matrix can be given a normal matrix A, I can find a unitary matrix U such that A star AU is diagonal. So this is the spectral theorem for normal matrices. And I think this is a good place to stop this lecture. And this completes the proof of the spectral theorem in the most general setup for matrices. And in the next couple of capsules, we shall see some applications and examples. Thank you.